All right, welcome to the deep dive.
Yeah.
You asked us to explore quantum reality, and, well, that's precisely where we're going.
The mind-bending world of quantum reality.
Exactly. It
Yeah.
can feel like we're plunging headfirst into the unknown, right?
hmm
But our goal here isn't to drown in the dense physics. We want to resurface. We want to come back up with the most fascinating, understandable insights.
Absolutely. I think it's important to acknowledge upfront that the quantum world operates by rules that often seem to clash with our everyday experiences, which is precisely why it can feel so abstract and so difficult to grasp.
Yeah.
But the fascinating thing is that within these strange rules, we actually find profound clues about the very nature of reality and everything around us.
Yeah, so to guide our exploration, we're focusing on the transcript from the Merlin AI video. It's called Quantum Reality Will Make You Question Everything You Know. I mean, that title alone,
That's a great jumping off point. It's very evocative.
yeah, it is. It kind of hints at the core of what we're going to be talking
Yeah.
about, right?
Indeed. I mean, we're going to navigate concepts like superposition, the idea that things can exist in multiple states at once, the spooky interconnectedness of entanglement, the seemingly impossible creation of particles from nothing, the nature of time, the role our own observations play, and even venture into some of the more far-out implications, like the potential links to a holographic universe and the power of quantum computing.
So let's jump right in. Let's start with superposition. This is the idea that I think really kind of, kicks the legs out from under our classical understanding of reality.
Superposition, at its heart, suggests that a quantum particle, a very tiny particle, doesn't have a single defined state or location until we actually look at it, until we measure it. It exists in a kind of blend of all possible states simultaneously. Imagine it's like a spinning coin in the air. It's neither heads nor tails until it actually lands.
A good analogy. And a really classic way of illustrating this is the two-slit experiment, right? Can you break that down for us?
Certainly. So picture this. Imagine we're firing tiny particles towards a screen that has two narrow slits in it.
Okay.
Now, if we were dealing with everyday objects, like if we were shooting tiny marbles at these slits, we would expect to see two distinct lines on the screen behind the slits corresponding to the marbles that pass through each opening, right?
Yeah, makes sense.
Pretty straightforward. However, when we conduct this experiment with quantum particles, like electrons or photons, the particles of light, we get something truly astonishing. We observe what's called an interference pattern.
Okay.
And this pattern has these alternating bright and dark bands. And it's what you would expect from waves that have passed through both slits simultaneously and then interfered with each other. It suggests that each individual particle somehow goes through both slits at the same time, like a wave spreading out.
It's already getting weird.
Yeah.
So we have these particles, they're acting like waves, they're going through both slits simultaneously. But now, what happens if we actually try to observe which slit each particle goes through?
Ugh, this is where things get really interesting. The moment we introduce a detector to observe the particles at the slits, the interference pattern vanishes.
Wow.
We're back to just seeing those two distinct bands as if the very act of observation has forced each particle to choose a single path.
It's like they know they're being watched.
It's as if, right.
So it's like, okay, we're looking, that changes their behavior, right?
Exactly.
What does that even begin to tell us about the nature of reality?
It's one of the most fundamental questions in quantum mechanics. It suggests that at the quantum level, reality is not set in stone. It exists in a state of potentiality, a realm of probabilities.
Right. So let me ask you this. I mean, what does that then imply for the objects around us? I mean, like even just this chair I'm sitting on. I mean, is it truly in one definite location until I actually look at it?
That is the profound question that superposition forces us to consider. If the fundamental building blocks of your chair at the quantum level exist in this haze of possibilities, this blend of states, until observed, then perhaps the chair itself might also exist in a multitude of potential configurations until you interact with it.
Okay. That definitely makes you rethink the nature of reality, the solidity of things.
Indeed. This leads us to what is known as the Copenhagen interpretation. It's one of the most widely accepted but still debated ways physicists try to understand quantum mechanics.
Right.
It suggests that a quantum system exists in all possible states until a measurement is made, and then it abruptly collapses into a single definite state. The key takeaway here is that what we perceive as concrete, as definite reality, might not be so fundamental. Observation, interaction plays a far more active role in shaping reality than we typically assume.
Wow. Okay, my understanding of what is real has just taken a quantum leap into uncertainty. But the strangeness doesn't stop there, does it?
Yeah.
Let's delve into what's famously called spooky action at a distance,
Yeah.
quantum entanglement.
Ah, yes, entanglement. This is where two or more particles become linked in a way that's truly bizarre. They share a single quantum state, and what happens to one particle instantly affects the other no matter how far apart they are.
Okay, that sounds crazy, but can you give me a clear example of how that works?
Imagine two entangled particles, each with a property like spin.
Yep.
Spin is a fundamental quantum property. Think of it like a tiny internal rotation. If you measure the spin of one particle and you find it to be up, the spin of its entangled partner, even if it's billions of light years away, will instantly be down.
Instantaneously. That's what Einstein found so troubling about this, right?
Precisely.
He famously called it spooky action at a distance because it seems to suggest that information could be traveling faster than the speed of light, which, according to his theory of relativity, should be impossible.
Exactly. Entanglement poses a fundamental dilemma. It suggests that either information is indeed traveling faster than light between these linked particles, or the principle of locality, the idea that an object can only be directly influenced by its immediate surroundings, breaks down at the quantum level. It challenges our intuitive understanding of space and separation.
Yeah. And this isn't just theoretical, right? I mean, there's actually experimental proof backing up entanglement.
Absolutely. There have been numerous experiments. The work of physicist John Bell, in particular, provided a way to experimentally test whether entanglement could be explained by local hidden variables, the idea that the particles have predetermined properties from the start, we just don't know them.
Right.
Experiments based on Bell's theorem have shown, consistently, that entangled particles behave in ways that classical physics, with its reliance on locality, simply cannot explain. Measurement has a fundamental, and what seems to be non-local, effect on these quantum systems.
It sounds like these particles are linked in a way that just goes beyond simple cause and effect. It's not like one is sending a signal to the other.
Exactly. Their fates are intertwined at a deeper level than classical physics would allow. And this has a lot of practical implications. For instance, one of the most exciting is the development of a secure quantum internet, which would rely on the properties of entangled photons to transmit information in a way that is, at least in theory, unhackable.
That's fascinating. You also mentioned some broader philosophical implications that go beyond just technology, right?
Yes. I think entanglement raises some profound questions about the nature of reality itself. Research by physicist Holger Hoffman, for instance, suggests that the reality of an object isn't something isolated or inherent, but is actually defined by its relationships with other objects.
Interesting.
It challenges the idea of a purely objective reality, independent of any interaction or observation. This interconnectedness that we see in entanglement, this non-locality, points to a universe where the role of the observer, the role of interaction, is far more central than classical physics ever suggested.
Right. It really sounds like the observer isn't just passively witnessing reality, but they're an active participant in defining it.
Precisely. And entanglement really amplifies this idea, suggesting that what one observer perceives as the state of a system can be fundamentally linked to the measurements made by another observer, even if they are separated by vast distances. It points towards a universe where interconnectedness and the role of observation are far more fundamental than we typically imagine.
Okay. Get ready for another mind-bending concept. The idea that particles can just pop into existence from seemingly nothing.
This is the Schwinger effect.
That's right, the Schwinger effect.
Yeah. It describes the spontaneous creation of particle-antiparticle pairs from a strong electromagnetic field in what we perceive as empty space. It forces us to completely reconsider our definition of a vacuum and the very origins of matter itself.
So you're saying that our everyday understanding of a vacuum is just, empty space is just wrong.
Completely off the mark in the quantum realm.
Okay.
In quantum field theory, the vacuum is not empty. Instead, it's the lowest energy state of quantum fields that permeate all of space.
Okay.
These fields are constantly fluctuating, giving rise to what are called virtual particles, which pop in and out of existence for incredibly brief periods.
They're just fleeting quantum blips.
Exactly. Now, the Schwinger effect demonstrates that if you apply a sufficiently strong electromagnetic field to this vacuum, you can provide enough energy to promote these virtual particles into becoming real, stable particle and antiparticle pairs. In essence, you get something from nothing.
That's pretty wild. And how does that change how we think about the origin of the universe?
Well, it suggests that the universe has an inherent capacity to generate matter from what appears to be empty space, fundamentally altering our view of material reality and its genesis.
Yeah.
And again, this isn't just theoretical speculation. Recent research has achieved the spontaneous creation of electron-positron pairs in laboratory settings using materials like graphene and intense laser fields.
Really?
Yes. Furthermore, something called the Casimir effect provides indirect evidence of this energetic nature of the vacuum. It demonstrates that even in the absence of matter, tiny fluctuations in the electromagnetic field can create a measurable force between two closely spaced, uncharged conductive plates.
Wow.
This force arises from the virtual particles within the vacuum, providing a pretty clear demonstration that even seemingly empty space possesses this latent energy, this potential.
So what we perceive as a stable and unchanging reality, I mean, it's actually underpinned by this constant flux and this potential for creation.
Precisely. It highlights that our everyday intuition about the solidity and permanence of matter is really just a convenient approximation at the macroscopic level. It opens up some huge questions, though. Could this process have played a significant role in the very early universe, perhaps even in the Big Bang? Could it contribute to the observed imbalance between matter and antimatter in the universe?
These are some pretty huge questions that really challenge our assumptions about existence.
They do, and it really underscores the contrast with classical physics, where the conservation of mass and energy was a cornerstone principle. The quantum realm reveals that even these fundamental laws can be bent, albeit under very extreme conditions.
Right, so from particles popping into being, we're now venturing into even more, I guess you could say, speculative territory with this idea of quantum immortality and the multiverse. This sounds like something straight out of science fiction.
It does, but it arises from certain interpretations of quantum mechanics, particularly the many worlds interpretation. This interpretation proposes that every time a quantum measurement occurs, the universe doesn't collapse into one outcome. Instead, it branches into multiple parallel universes, each representing a different possible result.
So every decision, every quantum decision creates a split in reality.
Essentially, yes, leading to countless parallel universes.
Okay.
Quantum immortality then takes this idea a step further. It suggests that within this vast multiverse, every possible version of you exists. When you face a life-threatening situation where the outcome at a quantum level is probabilistic, your consciousness will always follow the branch where you survive.
So like the quantum Russian roulette thought experiment, you would always find yourself in the reality where the trigger doesn't result in your demise.
Exactly. From your perspective, you would never truly experience death because your consciousness would always find itself in a universe where you continue to exist.
That is wild. And this concept, it's obviously, I mean, it's not universally accepted within the scientific community, right?
No, it's highly debated and relies on interpretations of quantum mechanics that not all physicists agree with. Critics often point to the anthropic principle, which suggests that we observe the universe we do simply because it's the only kind of universe in which we could exist to make such observations. And they argue that this idea of quantum immortality might be more of a philosophical curiosity than a testable scientific theory.
All right, so definitely food for thought, even if it's in the realm of speculation. Now let's tackle another concept that seems to defy our everyday intuition: quantum time. And the idea that the future might somehow influence the past. How is that even possible?
I know, it sounds backward, right? Our classical understanding of time is linear. Events proceed from cause to effect, from past to future. But certain quantum experiments suggest that the relationship between cause and effect in time might be more complex than that. Let's revisit our old friend, the double slit experiment, but with a twist.
Okay, back to the slits.
Yes. Imagine that after a particle has passed through the two slits and has been detected, we then make a choice about whether or not to measure which path it took. The strange thing is that if we choose to erase the information about the path after the particle has already interacted with the detector, the wave-like interference pattern reappears as if the particle somehow knew in the past that its path information would be erased in the future.
Wait a minute. So a future action, like choosing to erase information, seems to retroactively affect the past behavior of the particle.
That's the implication. It suggests that our choices in the future might have a tangible influence on events that have already occurred in the past.
So does that mean that our decisions are predetermined, or is time just far more interconnected than we think?
These experiments raise profound questions about causality and the very nature of time. Some theoretical frameworks, like the block universe model, propose that all moments in time exist simultaneously, and our perception of a flowing present is just an illusion. Others explore the possibility of retrocausality, where effects can precede their causes under certain quantum conditions. There are even some theoretical connections being explored between parallel universes, with the idea that information might travel sideways in time between different realities. And of course, the observer effect might also play a role here, with our interventions potentially influencing both past and future states of a quantum system in ways we don't fully understand.
So it seems like the universe might have a much more fluid and less defined relationship with time than our everyday experience would lead us to believe. Okay, this is getting really deep and philosophical now. Let's explore an even more, I guess you could say, personal and unsettling idea. The role of consciousness in all of this. Could our minds be actively shaping reality?
This is a question that goes to the heart of how we perceive ourselves and our place in the universe. Some interpretations of quantum mechanics do suggest that consciousness might play a fundamental role in the act of measurement, which, as we discussed earlier, seems to collapse the wave function and bring about a definite reality. The idea that what we perceive as objective reality might be, in some sense, influenced by our minds is radical.
And this is what the Wigner's friend thought experiment highlights, right?
Exactly. It illustrates how different observers might have fundamentally different accounts of the same quantum system, suggesting that reality itself might be observer-dependent. And the relational interpretation of quantum mechanics takes us further, proposing that the properties of quantum objects aren't intrinsic, but rather arise from the relationships and interactions they have with other systems, including observers.
So could these quantum effects in our brains, could they explain some of the more mysterious aspects of consciousness, like our subjective experiences, or even phenomena like intuition?
Some researchers do speculate that quantum processes in the brain could provide a physical basis for these aspects of consciousness.
Interesting.
Maybe quantum coherence allows for a more integrated and holistic processing of information,
Yeah,
contributing to this feeling of unified awareness that we
I
experience.
see.
It's even been suggested that quantum phenomena might underlie intuition and creativity, allowing the brain to explore possibilities in a way that classical computation can't. And this has led to some intriguing, though still very speculative, quantum mind theories.
Quantum mind theories.
Yes, these theories propose that consciousness might not be simply a product of complex neural networks operating classically, but that quantum phenomena might play a fundamental role in its emergence in nature. Some even suggest that consciousness could be a fundamental property of the universe itself, rather than just an emergent phenomenon in biological systems. This perspective could link individual consciousness to a larger, perhaps universal consciousness. And of course, it ties back to the observer effect, suggesting that our minds might be active participants in shaping the reality we experience. This resonates with some ancient philosophical traditions that also saw consciousness as a primary aspect of existence.
It's astonishing to think that something as personal as consciousness could be so deeply interwoven with the fundamental laws of physics. Let's shift gears a little bit and talk about how these bizarre quantum effects might be playing out in the world around us, in nature, and specifically in the field of quantum biology.
It turns out that quantum mechanics is not just confined to the realm of the very small. It appears to be at play in some of the most fundamental processes of life, from the remarkable efficiency of photosynthesis to the navigational abilities of migratory birds, even our sense of smell.
Photosynthesis. How is quantum mechanics involved in plants converting sunlight to energy?
Research has shown that during photosynthesis, these packets of energy, called excitons, exhibit quantum superposition. This allows them to simultaneously explore multiple pathways within the light harvesting complexes of plants. This kind of quantum search enables them to find the most efficient route to the reaction center where the energy conversion actually takes place. And this results in an efficiency that surpasses anything classical physics would predict.
That's amazing. So light seems to have stumbled upon the power of quantum mechanics long before we ever even knew about it. You mentioned bird migration as well.
Yes, studies suggest that European robins, for instance, actually utilize quantum entanglement in specialized photoreceptor proteins in their eyes to sense the Earth's magnetic field.
How about that?
And this acts like a quantum compass, allowing them to navigate with a remarkable accuracy during their long migrations.
That's unbelievable. What about our sense of smell? How is quantum mechanics involved there?
Recent research indicates that the way we perceive different odors might actually involve quantum vibrations of those odor molecules, interacting with receptors in our noses. These vibrations could explain the incredible sensitivity and specificity of our sense of smell, going beyond just the shape of the molecules themselves.
Even within our own bodies,
Right.
with enzymes and biochemical reactions.
Exactly. The efficiency of enzymes, which catalyze almost all the biochemical reactions in our bodies, might be significantly enhanced by a process called quantum tunneling.
Okay.
This quantum effect allows molecules to pass through energy barriers that they wouldn't have enough energy to overcome classically, effectively speeding up the reactions that are crucial for life. It raises an intriguing question. Were quantum phenomena essential for the very emergence of life from non-living matter? And it also makes you wonder, how has natural selection actually shaped these quantum-level adaptations over the course of evolution?
Everything is just so interconnected. From the subatomic world to these entire biological systems, it seems like quantum mechanics is playing a fundamental role. Now let's move from the very small to the realm of cosmology and talk about the holographic principle.
Yeah.
The idea that our 3D universe might be encoded on a 2D surface sounds like something straight out of, well, science fiction.
It does, but it's a very serious theoretical concept that's emerged from the study of black holes and the information that they seem to contain. The holographic principle proposes that all the information that makes up our three-dimensional universe, including everything within it, could be completely described by information encoded on a two-dimensional boundary.
It's like a hologram, right?
Very much like a hologram. A hologram encodes a three-dimensional image on a two-dimensional surface.
And how did this idea even come about? How does this relate to black holes?
Well, the connection arose from attempts to resolve what's known as the black hole information paradox. The question was, what happens to the information about the matter that falls into a black hole? Is it lost forever? That would violate some fundamental principles of quantum mechanics. The idea emerged that when matter falls into a black hole, the information about that matter isn't actually destroyed, but it's encoded on the surface of the black hole, its event horizon. And calculations suggested that the amount of information a black hole can hold is proportional to the area of its event horizon, not its volume. Interesting. This hints at the possibility of this lower dimensional encoding. It suggests a deep connection between quantum mechanics, gravity, and the very structure of space-time, and implies that our universe might be fundamentally constructed from information.
And how might this holographic principle tie back to the quantum phenomena that we've been discussing?
Within a holographic framework, the seemingly spooky action at a distance of quantum entanglement, we talked about earlier, could be explained by this underlying two-dimensional information structure. What appears as non-local correlation in our 3D reality might simply be a consequence of how information is encoded and interconnected on this 2D boundary. This idea also points towards a potential path toward a unified theory of everything that could connect quantum mechanics and Einstein's theory of general relativity.
Okay.
Because both might arise from this fundamental information-based description.
Very interesting. Now, if the quantum world is so full of these strange effects, why don't we observe them in our everyday lives? Why doesn't my coffee cup exist in multiple places at once? That brings us to the concept of quantum decoherence, right?
Exactly. Decoherence acts as this bridge, or perhaps a barrier, between the quantum realm and the classical world that we experience. It explains why we don't typically see macroscopic objects exhibiting quantum behavior.
So what exactly is decoherence?
It's the process where a quantum system loses its quantum properties and starts to behave more classically because of its interaction with its surrounding environment. At its core, it's a process of entanglement, but entanglement with the environment. When a quantum system that's in a superposition of states interacts with countless particles in its surroundings, like air molecules, photons, radiation, it becomes entangled with them. This entanglement effectively spreads the delicate quantum information of the system out into the vast environment, making it impossible to isolate or observe the original quantum state.
I see. So it's kind of like Schrödinger's cat inside the box interacting with air molecules, radiation, the box itself.
Precisely. The more complex the system and the more it interacts with its environment, the faster this decoherence process happens. For macroscopic objects, like us and everything around us, this interaction is happening constantly with huge numbers of environmental particles, and this process happens almost instantaneously. So even a tiny dust particle floating in the air is going to decohere incredibly rapidly due to collisions with air molecules, which explains why we don't see it in a superposition of states.
I see. So our everyday world appears classical because these quantum states are constantly being disrupted and forced into single outcomes by interactions with everything around them.
Precisely. Decoherence also plays a role in our understanding of the measurement problem in quantum mechanics. When we perform a measurement on a quantum system, we're forcing it to interact with a macroscopic measuring apparatus. And this interaction leads to rapid decoherence of that quantum system, collapsing that superposition of states into a single definite outcome that we can observe. So it suggests that the classical world that we perceive isn't fundamentally separate from the quantum world. It emerges from the quantum world through this continuous process of environmental interaction and information dispersal.
So even the chair I'm sitting on, while it appears solid and in a fixed location, at a fundamental level, it's just a spread of probabilities, but its interactions with the environment are forcing it to behave as if it's in one location.
That's a very accurate way to understand it. Interestingly, some physicists also believe that decoherence might play a crucial role in establishing the arrow of time, the reason why time seems to flow in one direction. That the irreversible spread of quantum information into the environment could be linked to the thermodynamic arrow of time.
Wow. Now for a seemingly random connection, we have this idea of the golden ratio appearing in quantum mechanics. This feels more like art and aesthetics and natural patterns than fundamental physics.
It does seem like an unexpected connection, but the golden ratio, which is this mathematical constant approximately equal to 1.618, has been admired for centuries for its aesthetic properties. You see it in art, architecture, and its prevalence in natural patterns. But its appearance in quantum mechanical calculations is a surprising and intriguing development.
So where exactly is this golden ratio popping up in the quantum world?
Well, recent research has actually found the golden ratio appearing in the magnetic resonance of spins in cobalt niobate crystals. This is a quantum material. Additionally, the golden ratio is very intricately linked to the geometry of a very complex eight-dimensional structure known as the E8 lattice. This E8 lattice has been proposed as a potential underlying framework for unifying all the fundamental particles and forces in nature. And the fact that the golden ratio, with its very deep mathematical properties, manifests within this structure suggests that the properties of particles might actually arise from deep geometric relationships within a hidden, higher dimensional reality.
So it's almost like the universe is speaking to us in this language of mathematics in these unexpected ways.
In ways that we're still trying to decipher.
Yeah, exactly. And finally, let's turn our attention to a field that really promises to harness the power of quantum mechanics for, I guess you could say, revolutionary technologies, quantum computing.
Quantum computers represent a paradigm shift in computation. They leverage these bizarre and counterintuitive but very powerful principles of quantum mechanics, like superposition and entanglement, to perform calculations that are beyond the reach of even the most powerful classical supercomputers.
I see. So what is the fundamental difference then between a regular computer and a quantum computer?
Well, a classical computer stores information as bits, which, as you know, can be either a 0 or a 1. But a quantum computer uses qubits, and thanks to superposition, a qubit can exist in a combination of both 0 and 1 simultaneously. This ability to represent and process multiple states at once allows quantum computers to perform calculations in a fundamentally different and potentially much more powerful way. They also exploit quantum entanglement to do coordinated operations on multiple qubits.
So for certain incredibly complex problems, a quantum computer could find a solution exponentially faster than a classical computer.
Yes, that is the theoretical promise. Imagine a problem that involves exploring a massive number of possibilities, like trying to simulate the behavior of complex molecules for drug discovery. A classical computer would have to examine each possibility sequentially, one after another. But a quantum computer, using superposition and entanglement, could theoretically explore all those possibilities at the same time. This opens up the potential for breakthroughs in fields ranging from material science and artificial intelligence to cryptography and beyond.
It sounds very transformative. But I know that quantum computing is still a relatively young field. What are some of the hurdles that need to be overcome?
The challenges are significant. Quantum states, as we've been discussing, are extremely fragile. They are highly susceptible to decoherence, and maintaining the fragile quantum states that are necessary for computation for any significant length of time requires incredibly precise control and near-perfect isolation from any kind of environmental noise. Building scalable and fault-tolerant quantum computers is a huge scientific and engineering undertaking. And of course, developing a truly robust quantum internet, which would rely on the secure transmission of information via entangled photons, also depends on overcoming a lot of very difficult technological hurdles.
So it's definitely an exciting frontier, with the potential to completely change the world as we know it, even if there are still significant obstacles to overcome. Well, we've covered a lot of ground today. It's been quite a deep dive into this extraordinary world of quantum reality.
We have. We've journeyed through superposition and entanglement, explored the creation of matter from nothing, pondered the perplexing nature of time and the role of the observer, and even touched upon the implications for biology, the holographic principle, and this incredible future of computation. Quantum mechanics offers a view of the universe that is far stranger and more interconnected than we could have imagined based on our everyday experience.
It really makes you rethink some of our most basic assumptions about the nature of reality, consciousness, and our place in the universe. The universe that we experience might be a far more fluid, far more participatory reality than we typically imagine.
Precisely. So as you go about your day, I encourage you to think about these quantum concepts. Consider how they might subtly shift your perspective on the world around you, the choices that you make, and the very fabric of your existence. Perhaps the universe holds even more wonders and mysteries than we can currently grasp.
Well, that's it for this deep dive into quantum reality. We hope you found it enlightening. We hope you found it mind-bending. And be sure to let us know what other fascinating topics you want us to explore.
Until next time.
Until next